Today, I want to explain Taylor and maclaurin series. What is Taylor series and what is maclaurin series? Taylor series is a series solution of a function centered at x equals a. For instance, our Taylor series is given as summation n equals 0 to infinity, and we have our fn of a all over n factorial x minus a raised to power n. Let me call this equation 1. So this is our Taylor series. So a Taylor series is a series solution of a function. Now, what is maclaurin series? Maclaurin series is a special form of Taylor series. All maclaurin series are Taylor series, but not all Taylor series are maclaurin series. For maclaurin series, we have summation n to be equal to 0 to infinity, while our fn of 0 all over n factorial x raised to power n. Let me call that equation 2. So what is the difference between equation 1 and equation 2? So for a Taylor series is always centered at x equals a. Why for maclaurin series, our x equals 0. So that is the difference between maclaurin series and Taylor series. For maclaurin series, x is always equal to 0. Why for maclaurin series, our x equals a. So I want to solve examples on maclaurin series. How do we use maclaurin series to solve series solution of a function? For instance, if we are given f of x to be equal to exponential raised power s, how do we use maclaurin series to solve this? So the first thing is to differentiate this. We have f prime of s to be exponential raised power s. For the second derivative, same thing. Y for the third derivative, same thing. We have exponential raised to power s. Now, what's maclaurin series? According to the definition I did earlier, I said for maclaurin series, x is always equal to 0. So if s equals 0, f of 0 will be exponential raised to power 0, which is 1. F prime of 0 will be exponential raised to power 0, equals 1. F double prime of 0 will be equal to exponential raised to power 0 equals 1, and so on. Now with this, we can now obtain our series solution. Now for our series solution, we have exponential raised to power s to be equal to f of 0 plus f prime of 0 1 factorial s plus f double prime of 0 2 factorial s squared, and so on. So our exponential raised to power 0. So what's the value of our f of 0? 1. So we have 1 plus, what's the value of f prime of 0? 1. So we have 1. Because we have 1 factorial here, 1 factorial is what? 1. And s is here, we have s. Plus f double prime of 0 is also 1 all over 2 factorial, and we have s squared, and so on. So our exponential raised to power s will be 1 plus s squared all over 2 factorial. This is the first term, the second term, the third term. Even the fourth term will also be s raised to power 3 raised to over 3 factorial, and so on. So this is our series solution of an exponential function. Thank you. Now, this is another example on a function using maclaurin series to find a series solution to this function. How do we go about this? We are given a function to be equal to sine s. So let's do our first derivative. When you differentiate sine s, we have cos s. Now for the second derivative, if you differentiate cos s now, we are going to have minus sine s. For the third derivative, when you differentiate sine s now, we have what? Cos s. So because there's a negative sign here, we have minus cos s. So we can continue differentiating in this manner. But let's stop at this third derivative. So don't forget, these are our functions, sine s. We differentiate sine s, we have cos s. We differentiate cos s, we have minus sine s. We now differentiated sine s again, we have cos s. Because of this negative, we have this. Now, for Maclaurin series, we said s is always centered at 0. So when s equals 0, our f of 0 will be, sine 0 is what? Sine 0 is 0. For the first derivative, cos 0 will be 1. For this one, for the second derivative, sine 0 is 0, so this will be 0. Why this will be, for the third derivative, that will be minus 1. So these are the values we are going to use to get our series solution. So for Maclaurin series of sine s, that will be equal to f of 0 plus f prime of 0, 1 factorial s plus f double 0, 2 factorial s squared plus f triple prime of 0, 3 factorial s cube. So our sine s here will now be equal to, our f of 0 is what? 0. So we don't write this. Our f prime of 0 is 1. So this is 1. 1 times all this will give us s. Plus, for the second one is 0. So we are not writing this. For the third one, we have minus 1. 1, 2, 3. So this one we cancel out is 0. For the second one is 1. We have this. For this is 0. So we write the third one, which is minus 1. So we have minus s cubed over 3 factorial. If you look at this pattern, a sine function is what? They are odd functions, which implies that all the even numbers will be 0. So if we are doing this, the third value here will be x raised to the power 5 all over 5 factorial. Why the sixth one will be 0? The seventh one will be minus x7 all over 7 factorial. So this is our series solution, or Maclaurin series solution to a sine function. So today I want to explain how to use Taylor series to expand a function and what actually differentiates Taylor series from Maclaurin series. Now, look at this function, natural logarithm of s. You can never use Maclaurin series to expand this. Why? Because for Maclaurin series, s is always equal to 0. Now, if you put 0 here, all the derivative here will be undefined. So in that case, we are going to use Taylor series to expand this function. So when you are using Taylor series, you will be given a point. At this point, s equals 1. S equals 1. In some other cases, it might be another value. But in this case, we are giving s equals 1. So anytime s equals 1, we are saying our a equals 1. This one, a equals 1. Now, how do we expand this? I've already differentiated all the function. Our f of s is ln s. If you differentiate it, you have 1 over s and so on. Now, since s equals 1, anywhere you see ln x here, we put 1. So ln 1 is 0. Putting 1 here, 1 divided by 1 is 1. Minus 1 all over 1 will give us minus 1. And here we have 2. Now, using Taylor series expansion. For Taylor series expansion, we have our f of a plus f prime of a 1 factorial x minus a raised to power 1 plus our second derivative of a all over 2 factorial x minus a raised to power 2 plus our third derivative of a all over 3 factorial s minus a raised to power 3. Now, let's make our substitution. For f of a, don't forget that our a is 1. So this will give us 0. Automatically, we don't need the first term. For the second one, f prime of 1 is 1. So the whole of this will be 1. So we are left with s minus a. Don't forget that our a is 1. So this will be s minus 1 plus f double prime of a is minus 1. So it will affect the positive sign here. So this will be minus s minus a all squared over 2 factorial. For the third one, we have 2. So this will be what? Plus 2 s minus 1 raised to power 3 all over 3 factorial. So this is the series expansion using Taylor series. Now this can be written as our lane s is s minus 1 minus s minus 1 all squared over 2. 2 factorial is 2 plus s minus 1 raised to power 3 all over 3 and so on. So this is Taylor series expansion of natural logarithm of s. So this actually differentiates Maclaurin series from Taylor series, because you cannot use Maclaurin series to solve this, because whenever the value of s is 0, all the function will be undefined. So this is what we have here. So what we did here is 3 factorial is 6. So 2 goes in 6 will give us 3. That's where we obtain this 3 form. Thank you.